All right, let's get into day 10 advent of code. We didn't do too well on day 9, only had 1 star, but we're going to get day 10 today. Hopefully, we're successful. We have a bunch of people in the chat who are actually pretty good at lead code, so they'll help us out if we ever get stuck. But let's get it. Like and subscribe if you're not already subscribed to the channel. But all right, day 10. Let's lock in. Day 10 factory. Just across the hall, you find a large factory. Unfortunately, the elves here have plenty of time to decorate. Or fortunately, the elves here have plenty of time to decorate. Unfortunately, it's because the factory machines are all offline and none of the elves can figure out the initialization procedure. The elves do have the manual for the machines, but the section detailing the initialization procedure was eaten by Shiba Inu. All that remains of the manual are some indicator light diagrams, button wiring schematics, and Joltage requirements for each machine. So we just have a bunch, like a sequence of stuff. The manual describes one machine per line. Each line contains a single indicator light diagram in square brackets, one or more button wiring schematics in parentheses, and Joltage requirements in curly braces. To start a machine, its indicator lights must match those shown in the diagram. To start a machine, okay. Where dot means off and hashtag means on. The machine has the number of indicator lights shown, but its indicator lights are initially turned off. So an indicator light diagram looks like this, means that the machine has 4 indicator lights which are initially off, and that the goal is to simultaneously configure the first light to be off, the second light to be on, the third to be on, and the fourth to be off. Okay? Let's see. You can toggle the state of the indicator lights by pushing any of the listed buttons. Each button lists which indicator lights it toggles, where 0 means the first light, 1 means the second light, and so on. When you push a button, each listed indicator light either turns on if it was off or turns off if it was on. You have to push each button an integer number of times. There's no such thing as 0.5 presses, nor can you push a button negative number of times. Bruh. So button wiring schematic like 034 means that each time you push that button, the first, fourth, and fifth indicator lights would all toggle on and off. If the indicator lights were like this, pushing the button would change them to be like that. Okay? Because none of the machines are running, the joltage requirements are irrelevant and can be safely ignored. Okay, we can just ignore the joltage for now. Maybe that might be another thing in the future. You can push each button as many times as you'd like. However, to save on time, you'll need to determine the fewest total presses. I'm already sticking some dynamic programming thing. You will need to determine the fewest total presses required to correctly configure all indicator lights for all machines in your list. There are a few ways to configure the first machine. You can press the first 3 buttons once each, a total of 3 button presses. You could press 1 3 once, and 2 3 once, and 0 1 twice, a total of 4. Okay. And you can press all the buttons except 1 3 once. Okay. However, the fewest button presses required is 2. One way to do this is by pressing the last 2 buttons. So if we press 0 2. No, I didn't look at part 2. We're on the next question now, Paul. Day 10. Looks like some dynamic programming. The third machine has a total of 6 indicator lights that need to be configured. 1 2 3 4 5 6. The fewest presses required to correctly configure it is 2. One way to do this is by pressing buttons 0, 3, 4, and 0 once each. So the few button presses required to correctly configure the indicator lights on all the machines is 2, 3 plus 2 equals 7. Analyze each machine's indicator light diagram and button wiring schematics. What is the fewest button presses required to correctly configure the indicator lights on all the machines? Okay. Ooh, that's... Okay, the input is not too crazy. But we literally need to do it for every single one. Interesting. Robin, go try. You should try it out too if you're on your computer. So, dude, this one from yesterday was haunting me. Have you already looked at this one, Robin? The L's do have the manual for the machines, but the section detailing the initialization was in. Okay. One machine per line. Each line contains a single indicator light diagram, one or more button wiring schematics, and Joltage. We don't care about the Joltage requirements right now. To start a machine, its indicator lights must match those shown in the diagram. Okay, so it needs to eventually get to this. The machine has the number of indicator lights shown, but its indicator lights are initially off. So an indicator light diagram like means that the machine has 4 which are initially turned off, and that the goal is the first light to be off, second to be on. Okay. So everything. So let's take some notes. Again, not that straightforward right away, but we'll work through it and figure something out. It was hard, huh? I've never tried it yet. So we're gonna be given something like this. Let's look at one input. And we essentially we start with everything off. They said the fewest button presses required is 2. One way to do this by pressing the last 2 buttons. So the fastest ways to go from there's these 3 dots to 0 and 2. We get this. And then to 1 like this. Oh, sorry. And then 0 and 1 we get what? Like something like that. And then that matches. So these are kind of like the options of like combinations we need to do. So one way I'm thinking is Caesar mods in the building. So one way we're thinking is, could you just press like there's no reason to turn on 3. We essentially have this starting state and we eventually want to get to some end state, and we just need to follow. It might be like a graph question. Yo, Mod, thank you. Thanks for the $2 gifted. Appreciate you. Mod's funding my streaming career. Let's see. Mod, what are you up to? We're running 2K tonight? So if we do, I guess from the start, let's look at this. I guess like from the start, we have multiple options. We can like push button one. Say this is button one, this is button two, this is button three, this is button four, this is button five, button six, button seven. One way we could do is like we can try pressing button one, button two, like brute force three, four, like all the way, all the different options up to nine. I guess like here we can like also push all the buttons again, but it wouldn't really make sense to push the same button again because then we'll just go back to the same state. But I guess if we get back to the same state, maybe we could just cache that. And like for each one, like if we want to get to this state, we can get to 0. We could store a minimum of how we can get to each state. And if we ever get to a state higher, then we just return. If we can get to a state lower than we did before, then maybe we just keep going. But like the most brute force solution is like avoid getting back to the same state and like sort of like for each button like branch out all the different options. Like kind of it's essentially like a brute force, but we need to have a way to like not run it forever. Or I guess we could just brute force the whole thing. But like how do we know when to stop looping? Well, since we're minimizing, if we get to a state that we've seen before, like can we even just do a backtracking? Yeah, let me think about this a bit. So what are the different options? We can when we start with dot dot, we can start with just 3 or 3. Yeah, but there's no point in like pressing it back again, so because we'll just get back. But what if we only had these buttons and we just wanted to get 1 3? So maybe one option would be click, or we just want to get one. Maybe one option is click 1 3 and then click 3 again to turn just 3 off. Then we get just the dot, or we only get this one turned on. Why do you think we only need to press it once or twice? Okay, let's try brute forcing. Let me think of a brute force solution first, then we could figure out how to optimize it. So the main thing when it comes to brute forcing the algorithm right now, like it could be like a backtracking sort of recursion. And then maybe if we get to a state that we were at before, we just like, what if we get back to a state that we were at before? You don't need to press twice subsequently, but like maybe you can like, maybe there's a case where if you press it three times, given some sort of sequence, it might work. Because the way I'm thinking about this is like it's kind of a graph. When you start off on this state and you have multiple branches that leads you into like other states. Like you can get dot 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 hashtag. This is one state. You could eventually get back to this state. But maybe we just store that then we can see. Wait, maybe what we can do is let me think about this. Robin, I'll look at your suggestions in a second after I think about it for myself for a bit. The third machine has total 6 indicator lights that need to be configured. Okay. That's the hard part. Or you can press the first three buttons once each. A total of you can press 3, 1, 3, and then 2. You can press where 0 means the first light means okay. When you push a button, each listed indicator light either turns on if it was off or turns off if it was on. You have to press each button at an integer number of times. Okay. We know for sure. We know like one thing we know for sure is we're gonna be able to get. It's kind of like a graph, but we don't want to get into loops. We don't want to get into loops. So I think what I'm gonna do to avoid getting into a loop is yeah, maybe I won't try pressing it twice. More than twice. What happens if you press it more than twice, like three times? Will that do anything? Like, will there be a case when I need to push it three times? Then we have dot, 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 dot. And my goal is, like, when will I have to push it to get to. So maybe, let me think about this. Yeah, it's definitely not just like a simple backtracking. Put some options. Put some options. Blanking out. Three. So let's just simulate this just to see what we're working with. So we can start with dot, dot, dot. You can first press the first three buttons, once each a total 3 buttons. So we can go 3. That gives us, turns on this. Then we do 1, 3. Sorry, 1, 3. 1, 3. Turns this off. But like our 1, 3, that turns this off. We just do 2. Maybe we can be smart. Like we only want to turn ones on. We need to look at the ones we need to get in the right place and only click buttons that will lead us towards like closer to the result. Because we need to avoid. Okay, that's 3. Okay, that's example 1. Or you could press 1, 3 once. So you can start dot, 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 dot. You could press 1 and 3. 3. 2 and 3. This turns this off. And 0 and 1. Why does it matter? We already got there. Well, we press 1 and 3, 2 and 3, and 0 and 1 twice. Why would we need to hit it twice? That might be a hint. Okay, that's 4, yeah. Or you can press, that's example 2. Or you can press all the buttons except 1 and 3 once each. So we can start. So we can start with 3, 0, 1, 2. So from each state, let me think. I guess from every state, we can just try every option once. If we go from every state and try every option once, it's gonna deterministically get us to a different state. Yeah, we can try for everyone. Just try every button once, cause Coming from like suppose we're at this state and we tried all these different options once, it'll deterministically get us to a similar state or like to like a different state. Then we could kind of maybe just keep tracking a hash map, like the lowest that we've ever seen on any state. And then like for every single state, we could just try every single state we've seen, we could just try all of the options. Like for every single state we see, we can try all of the options, and that's all we need to do. Every time we see a new state, maybe we push it in a queue and we try all the different states with that option. Yeah, I think that might just be the solution right there. Every time we see a new state, we try all the different button combinations on that state. If we see a new state that we've never seen before, then we add it to some sort of queue. And then we just keep track of like for every state that we see, what's the minimum we've ever seen it get there. I don't know if that even makes sense. Does it make sense? Wait, let me think this through a little bit. How long we've been? 25 minutes on this one question. So pretty much what we do is start with starting state. Try every button combination on it. If we see like it will generate like X new states. For every new state, we generate for every new state we try every button combo on it. It's like a BFS. Do we need dices on this? Wait. No, like there's no weights. I think we could just literally do a BFS. And if we just like fan out like that, we're good. Okay. We'll try to like on this small example. So if we have something like this, we'll take. No way. I have a fire alarm going off. Not getting out. Okay. Expected. Maybe we could do expected state and just like put a tuple, which is like 0, 1, 1, 0. And then we could do the options. Dude, someone's fire alarm is going off. We can do. This could be the options like this, right? I don't know if y'all can hear in the background, but we're gonna still gonna get through this. definition. So we start with a state of 0, 0, 0, 0. Maybe you just do it people right here. Can you hear like the fire alarm going off in the background? I don't know whose is it. Bro, the fire alarm has just been going off constantly. Okay, good. I have like a good background noise. Yeah, Ramen, we could like bit mask. What do you mean bit mask the state? So we start with a Q and like wow. Scene equals set. Something like this. While the length of the queue. What we're gonna do is yeah, you're right. So yeah, I can try that out in a second. But what we said is what we're gonna do is we're gonna look through the options. So what we're gonna do is we're gonna be like candidate Q dot pop left, right? Since we're only we'll do import DQ. So this is the first state, and then we're gonna go for every option for option in options. What we're gonna do is we're gonna take like the and modified equals. We're just gonna turn the candidate into a list. Then for LM in the option, what we're gonna do is we're gonna flip it from 1 to 0. Yeah, maybe it's better for you. How do we flip it? Do we have to do like a XOR? Or we'll just flip it if for element like if 0 if 1 else 0. So if it's equal to 1, turn it to 0. If it's equal to 1, turn it to 0. Otherwise, convert it to 1. If it's equal to 1, turn it to 0. Otherwise, 0, then turn it to 1. If tuple, if can modified, in scene, continue. We'll have a distance here. Right? Set distance. Then we'll do Q dot append canned or modified distance plus 1. It's like we're doing a bunch of conversions, so it might be annoying, but and then we do can modified equals. So let's just turn it into a tuple right away. Distance plus 1. If candidate candidate canned equals expected state, break this. CD data on 3 part. For option in options. Let's see. Well, it's supposed to be a tuple. Aren't tuples iterable? Three, okay. Print the options real quick. 3, 1, 2, 3. Oh, okay, that's annoying. Like if it's a tuple. It's gonna turn these options into just arrays. Oh, I see. You're right, you're right, you're right. Smart, smart. I'll probably just like when I do the input. Okay, we're printing out the right result. Let's see if we're. What's the result here? What if we want to the one we choose by pressing? Okay. So now we just need to like generalize this input. So what we need to do is be able to like take the input string, split it. Um, I'm gonna grab my code that reads from the input. What? Oh, test for line in input string, print the line. Then we're gonna put this all into like some function at some point. Ramen, what do you think so far about the solution? Is this similar to what you would have tried? For line and input string. What the? Why is it all in? Oh, I didn't split it. So what we're gonna do is for line and input string, what we're gonna do is part one or parts equals line dot split by just like we just split by the spaces. And then what we say, what was this? Expected state. Expected state equals parts at 0. And then we have buttons equals parts from 1 to -1. And then we have, what's this last part? Joltage equals parts at just like the last element. So let's just make sure we're extracting the expected state in buttons. Perfect. Now we just need to turn the expected state into what we want. So we just want it to be a tuple like this. So we can do is parts equals if if lm is equal to hashtag, that means it's on, turn 1, else 0. So we just want to create the tuple like this. Oh, and we're gonna go 1 to -1 because we're gonna ignore the brackets. So we this is the expected state that we want to get into. Now we want to turn the options into tuples. Wait, what are we doing? Because we're just getting 1 and 3. This is how we're gonna get the buttons. We're to get the buttons equals we're gonna get the parts again. when we get the actual buttons, what we're gonna do is we're gonna have an array. Like for elem in button string, we're gonna get button int equals elem dot split. But we're gonna go 1 to -1. And we're gonna split by comma. Then in buttons dot append, we're gonna turn this into a tuple, and we're gonna put the button int. And now buttons should show up how we want it. For elem for x in. We're gonna convert this. We need integers. Perfect. So now we're gonna call this like BFS, and it's gonna return us the result. We're gonna create a BFS here. We're gonna see our expected state. We're gonna be passed in our options, which look good now. Goes I in range length of expected state. We're gonna start this off with 0. We return that to a tuple. So we're just gonna do that, and we're gonna be like, for every line, what we're gonna do is we're gonna print BFS expected state button 232. Perfect. Now we just add them up. We just add them up like that. Print the result. Now we have 7. All right. Now let's get the puzzle input and see how it performs. Woo! That was quick. One gold star. Let's go. BFS. All right. Dub. Okay, let's try out level 2. Let me get some water. Yo, chat. What do y'all think? That was good. That took me 50 minutes to solve that question, but once we figured it out, code was easy. Okay, take a read at this real quick. I'm grabbing some more water. All right, part two. All the machines are starting to come online. Now it's time to worry about joltage requirements. Each machine needs to be configured exactly to the specific joltage levels to function properly. Below the buttons on each machine is a bigger lever that you can use to switch the buttons from configuring the indicator lights. Yeah, what were you thinking for that one? Wait, let's look at the joltage. Okay, that's what joltage looks like. Each machine needs to be configured to exactly the specified joltage levels to function properly. Below the buttons on each machine is a big lever that you can use to switch the buttons from configuring the indicator lights to increase the voltage. Each machine needs to be configured to exactly the specified joltage levels to function properly. Below the buttons on each machine is a big lever that you can use to switch the lever. Below the buttons on each button. Below the buttons on each machine is a big lever that you can switch the buttons from configuring the indicator lights to increasing the joltage level. We have to ignore the indicator light diagrams now. The machines have a set of numeric counters tracking its joltage levels, one counter per joltage requirement. The counters are initially set to 0, so joltage requirements like 3, 5, 4, 7 mean that the machine has 4 counters, which are initially 0. And that the goal is to simultaneously configure the first counter to be 3, the second counter to be 5, the third counter to be 4, and the fourth to be 7. Is this like some backpack problem? The button wiring schematics is still relevant. In this new Joltage configuration mode, each button now indicates which counter it affects. Where 0 means the first counter, 1 means second, and so on. When you push a button, each listed counter is increased by 1. So a button wiring schematic like 1, 3 means that each time you push that button, the second and fourth counters would increase by 1. If the current Joltage levels were 0, when pushing that button would change them to be 0, 2, 2, 4. You can push each button as many times as you like. However, your finger is getting sore from all the button pushing, and you'll need to determine the fewest total presses required to correctly configure each machine's joltage level counter to match the specified joltage requirement. Consider again from an example. Is it just a continuation of the same one from last time? Configuring the first requires a minimum of 10 button presses. Could you do a BFS again? Because a minimum of 12 button presses. One way to do this by pressing 3 once, 1, 3, 3 times. Okay, we just need to keep clicking them up until they get here. Okay, let's just try brute forcing on this very small example. Day one, day one, or sorry, day 10, part one done. Why can't we just do the same thing? Eric, how did you solve the first part? Did you also use a BFS? Or you did a backtracking? What we can do is like for the joltage, get 1 to -1. Yeah. 10, 11, 15. A split. Can we just do this? Can I do part 2? So what we're gonna do is print the joltage and the buttons option. So we're trying to get to 35471. So we start off with a tuple with everything starts at 0. Then we say scene is at 0. Then we add that. If the expected state does this even end? Oh, does. Oh wait. Is that a for loop? Wait, I'm just trying to think of this. Am I like in a Oh, okay. If candidate modified at the LM is greater than like expected state, we couldn't even get to the expected state. Like, can we just could we just use the same algo as before? But instead of joltage, like we're just bumping up. How can it not can't how can it not find? Oh, because I put like a background noise filter. Cause it's so loud outside sometimes. Can you hear it now? There was a lot of sirens and there was a lot of fire alarms. Okay, let's see what happens after the first loop. Do you use like some matrix multiplication then? Or like, let's see. Wait. Um, what's RRF? And then backtracking from for non-pivots. I can't even get my normal solution to work. What kind of reduce row echelon? I have no idea what that is, man. Are you a competitive programmer? Y'all see what I'm doing wrong here? Wait, Q. Oh yeah. I remember that. That being like a. I remember that reduced row echelon. Now that you mentioned it, for element option. Oh, this not. if I is greater okay, I'll take a look at that in a sec. If why can't it find on this simple example? What am I doing wrong? So if we're starting with the candidate. It should be like all zeros. Oh, will it ever match? Okay, we'll think about the linear algebra one in a second. But like, if this is gonna return me like 357. Okay, the start should be for I in range. Okay. Honestly, we don't even care about like the joltage on the other. Like we don't. One thing we don't care about the joltage on the other ones because. Let me debug this. Expected state 350. Start. We start with 0, 0. Break after the first loop. Four. Why is my just like my simple equation not working? Print. What am I doing? So what we're doing is we're doing what's the goal? The goal is 3574. Oh, I'm so dumb. This should be a tuple. Holy. So you can tell I'm cooked. Okay, then we're gonna try to figure out what the better solution in a sec. Let me try this. How long is it taking for each line to finish? Oh, it doesn't even get there. Can't even get the first one. Okay, how does the reduced row echelon work? Look at that. Dude doesn't even finish with the first question. Let's look up reduced row. Bro, what is this? No way. All zeros are at the bottom. Okay. The leading entry, first non-zero in each non-zero row is 1. Okay. Each leading one is to the right of the leading one in the row above it. Okay. I remember this. Each leading one is the only. Okay. Okay. Make the top entry of that column a 1. Use row to make all the... Where do I perform it though in my algo? Oh my god, this cooked. This is actually cooked. Damn. Eric, you're a legend. Yo, you are you part of the Discord? Let's see your code. I'm not gonna. If that's the only way to solve this question, I don't know if I can get it, man. But why do we even need that? Like, could you explain that? It's it's. Why do we need to get it into that form? Why is it? Like, what are we performing RREF on? Like, are we doing are we doing that reduced row echelon thing on these elements? Okay, that is actually wild. Yeah, but like, what are we performing it on? What's the input to the... Like, how do we build up this matrix? Like, what is the original matrix gonna be? Your backtracking solution drops. Interesting. Yeah, I remember this reduced row echelon form, but why do we care each? How do you mean by this? Equals 6. 2x plus 3y plus z equals 11. Negative. X equals 1, Y equals 2, Z equals 2. So it's like, from, okay, let me do debrief on approach for date, approach number 1. This is for day 9 real quick. Bro, you know how long it's been since I took Lin Alg? And that was literally my worst grade. Approach number 1. Let's see. There's the ray casting, then there's like the Green's theorem. Come. So you're saying for day 10 for part 2, what are people saying? You're backtracking? So basically, what does this guy say? Yeah. This is the hint I got. It's art, but like, I even forgot what. I need to figure this out. Equals 6. Dude, like I don't know. Paul, I'm gonna catch you in the office and we're gonna talk about this one for sure. I don't get what the input is supposed to be. Damn, they got us again, huh? They got me again. All right. I think this one is way out of my skill level. I need to go study some Lin Alg. But I'm happy we at least got the first question right because it's just basic algorithms like a BFS or backtracking. Well, yeah, like what we're gonna do is I'm not stopping until I solve part 1 and part 2. So if I need to study up concepts, I'm going to study up those concepts, and then we're going to attack like the part 2s and figure them out. Eventually, before the end of the year, we're going to make sure we finish like all these advent of code, and I'm just going to look straight off like just talking with people and trying to understand their solution. Bro, the math is just cooking me right now. Paul, we need to sit down and just debrief on this. I'm going to show you the question if you have time. Like, I'm just wondering, okay, what do we perform what do we even perform the operation on? But it's all good. It's all good. We gotta sleep. We gotta get ready for work tomorrow. Gotta be up early. I need to go study some linear algebra. Yo, chat. What should I study before like trying this question again? And I'll go watch some videos on it before I go to sleep. Just like straight up REF. Bro, like I don't know what we're backtracking on. Usually when you're backtracking, you're like trying you have like a state and then you're trying to modify the state, and if that state doesn't lead to a result, then you backtrack. Like what's a state that we're working with? That's the part that I'm like confused about. Yeah, it's cooked. It is cooked. Yo, you want the prompt? If you need to submit like my day 9 part 1, yeah. Yeah, if you want to just like submit my part 1, you can probably. If you want to just like get to the part 2, and then we could just like yeah, chat about this. Rough. Took it L. It's all good. We'll bounce back. We'll bounce back.